finally. So today, the good thing about this is, even though we're getting started late, this is a fairly short lecture, and it's a lecture on something you guys should already know quite a bit about, which is just the evaluation of integrals. And so this, out of all the lectures we're going to cover this semester, is probably the most review, the most lecture of something you guys have seen before. And the bottom line here is I'm going to teach you guys how to use this book and how to really get the most out of it, which is something you're going to be using throughout the semester. So when I started this class a few years ago, I included this not just because it was in Matthews and Walker, but because there's a lot of little things about integration that we tend to forget over time if we're not using this stuff every day. So basically, there's a lot of different ways that you can kind of use the book, use a guide. And we're going to use a lot of these techniques until we get into complex variables using contour integration. So this is basically everything that you're going to do with integrals short of that. So we talk about changing variables, for example. Let's say, as an example, you have the integral from 0 to infinity e to the minus t squared dt, and we know that's equal to 1/2 times the square root of pi. And we know that because it's in our Shom's outline handbook. Well, what happens is, if you know this, and you're given some integral, like 0 to infinity of e to the minus au squared du, and we want to solve this integral, then we can do it by just simply saying, well, that u times the square root of a is equal to t, and then du should be equal to 1 over square root of a times dt. And so if you do that, then you can plug this into this equation, and you can see that, well, this equation should read like integral from 0 to infinity of e to the minus t squared times 1 over square root of a dt, and which is basically just the same equation here, but with a 1 over square root of a, and that is then going to be equal to 1/2 square root of pi over a. So in other words, this is like the most common sense thing you can do, just taking your integral that you have, finding something that's similar that you know the solution to, and then just substituting away. Now, there's limits on this, of course, because what if you had the integral from 0 to infinity e to the minus u to the 4th u du? Well, this one, you have to be a little bit more creative, because if you look at the two, you could say, well, here your u is equal to t squared. Sorry, u squared is equal to t. Get that backwards. If u squared is equal to t, then 2u du would be equal to dt, and so then this equation can become the integral from 0 to infinity of e to the minus t squared, and then a factor of 1/2 dt, which is equal to 1/4 square root of pi. Okay? So that works. But what about if you had the integral like this? Which is basically the last one, only here I have t to the fourth instead of t squared. Well, in this case, you can't make this into the other integral. There's no way you can turn the t to the fourth into a t squared because the dt is also going to change. And so what you can do with this is you can look for another example, and you can look for something like, I'm going to call this I sub alpha, just a shorthand, is the integral from 0 to infinity of e to the minus t alpha dt. And so I just replace the 4 with the alpha, and then I get this one is just basically going to be I sub 4. So in this equation, if I take t to the alpha and I say that's equal to u, so that u to the 1 over alpha is equal to t, and then my dt should be equal to 1 over alpha u to the 1 over alpha minus 1 du. So if I plug that into the equation, I get I of alpha is equal to the integral from 0 to infinity of e to the minus u to the 1 over alpha minus 1 du. And this is all going to be multiplied by 1 over alpha from the du term. Now, if I look at this equation in my book, then I know that I can compare that to the gamma function. And the gamma function, by definition, is the integral from 0 to infinity of e to the minus u to the z minus 1 du. And so therefore, I could say that my I of alpha is just equal to 1 over alpha times the gamma function of 1 over alpha. So I didn't, in a strict sense, I didn't really solve anything. All I did was just sort of use the parallels between what I can look up in the handbook and what I see already. So it's the same kind of pattern recognition stuff that you did last week when we were talking about infinite series, in a way. The only difference is that, this is a little bit more generic, more general. And also teaches you that, this is a really useful book. This is something not expensive, a great tool to have. Another example is, let's suppose I have some integral I'm going to try to solve. It's the integral from 0 to infinity of e to the minus ax cosine lambda x dx. Now there's several different ways to solve this, and I'm going to use the first one. Now when you're solving the integral, remember what you're solving here is basically the area underneath the curve. And so what this is basically a dampened oscillator. So it's exponentially, it's something like this where it oscillates a sine wave, so it's symmetric, right? But it keeps getting smaller and smaller and smaller. So if you draw an envelope here, what's happening in this envelope is that it exponentially decays. So here, we want to integrate this thing And the easiest way to integrate it is to actually use what we know about complex variables. So we can take this and we could turn it into the real part of the integral from 0 to infinity of e to the minus ax times e to the I lambda x dx. So what I did was I basically took I took my cosine and I turned it into an exponential function. So when I do that, I can actually combine the exponentials together in my integral. So I have, I could say I lambda minus a times x dx. And then when I integrate this thing, I'm just integrating the exponential, so it's just now the real part of 1 over I lambda minus a times e to the I lambda minus a x. And I'm evaluating this thing from 0 to infinity. And so when I put in the 0, well, I put in infinity first, and you can see that this is going to disappear because I have the minus a, and if I'm assuming a is positive, then this is going to shrink away. When I put in the 0, the exponential term just becomes 1, and that kind of disappears. So this is going to be equal to the real part of 1 over a minus I lambda. And then to clean it all up, what you have to do is multiply top and bottom by the complex conjugate, and you're going to end up with a over a squared plus lambda squared. And the reason why you want to do that is because you have to take the real part, and you can't take the real part if there's an imaginary term in the denominator. So you have to rationalize the denominator. You can do the same thing if this were a cosine, or sorry, a sine. And so like if you had this integral, then that would be equal to taking the imaginary part of the integral and then when you take the imaginary part, you're doing the exact same integral here, only it's the imaginary part, and the imaginary part ends up giving you a lambda over a squared plus lambda squared. And so in doing this, you basically solve the integral once, and then you can apply the solution to the other one. Oh, because it's sine. And remember, exponential e to the I lambda is equal to cosine lambda plus I sine lambda.
And so you have to solve for both the real and the imaginary.
Well, you know, you can. Well, yeah. Well, what happens here before you solve for the real part? You actually got this term right here in the parentheses would actually be a plus I lambda over a squared plus lambda squared. So the real part will be the a term, the imaginary part is the lambda term. And that just comes when you rationalize it. Because when you rationalize it, what you're doing is you're multiplying top and bottom of this by a plus I lambda, since that's the complex conjugate as the denominator. Now another thing you could do with this exact same problem is we could take I equals the integral and we could turn it into two integrals, because now we can have it as e to the minus ax times e to the I lambda x plus e to the minus I lambda x over 2 dx. And if you do that, then now you have one integral, which is 1/2 e to the minus ax e to the I lambda x dx, plus the second integral, and then you can combine the terms and the exponentials again. So this first term, the first integral is going to be e to the, I'm going to keep it consistent, so I'm going to say minus a minus I lambda x. And the second one is going to be this one, e to the minus a plus I lambda x dx. And so when you solve the integrals, you're going to have one of these terms is going to go 1/2, and then you got your minus 1 over a minus I lambda e to the minus a minus I lambda evaluated from 0 to infinity. And the other one is going to be pretty much the same thing, but it's going to be an a plus I lambda Now here's the thing. When you put in the infinity terms, both of them disappeared because you still have the minus a in both terms, so they both shrink away to 0. It actually was infinity. So you end up with just the other one, so you have 1/2, and then this first one's just going to be 1 over a minus I lambda. And then you have the other one's going to be 1/2, and it's going to be 1 over a plus I lambda. And you know it's just no real and imaginary stuff here. And so then you just have to combine them. So when you multiply each one of these by its complex conjugate, you have 1 over a minus I lambda times a plus I lambda over a plus I lambda. And the other one, you're going to have 1/2, 1 over a plus I lambda, and you multiply it by its complex conjugate. And so the result is going to be 1/2, and then you have an a plus I lambda over a squared plus lambda squared, and then the other one's going to be a 1/2 a minus I lambda, and it's going to be a squared plus lambda squared. And you'll notice that the I lambda terms here cancel out, and the a terms add together, and you get the same result. So that's the exact same problem worked out 2 different ways, by just assuming that I'm going to take the exponential term and break it up, 2 completely different ways. And so I solved this without actually looking in the handbook, but it's still, you can see it's just basically just playing around with the exponential terms and changing it into a form where I could solve it. All right, now this is the part where I get to start showing you some tricks, now that we know how to do that one. So let's suppose you have the integral from 0 to infinity e to the minus ax cosine lambda x times x dx. So it's basically the same integral I just solved, only you have this extra factor of x in here. So what you can do is you can think of this as if I had just taken the previous integral and I had differentiated the exponential term with respect to the parameter a. So basically we can differentiate or integrate with respect to a parameter. And because each one of these is different, the differential commutes with the integral, and it can actually take a derivative inside of the integral, as long as you're not taking that derivative with respect to what you're integrating. So in other words, if I say that this is equal to the derivative with respect to a of the integral of e to the minus ax cosine lambda x dx, that's legit. Or I can even write it as the integral with respect to lambda of this exponential with a sign. Either one of those is going to result in the same integral. So if I know I can do that, where we just differentiate the entire integral, then what I can do is I know what the solution to this integral is. And so this is going to be equal to minus dA of a over a squared plus lambda squared. And the second one would be like taking d lambda of lambda over a squared plus lambda squared. And if I take the first one, I take that derivative, I do all my chain rule stuff, it's going to come out as a squared minus lambda squared over a squared plus lambda squared squared. And if I do the second one, I'm going to have the same answer. So either way, I can sort of play that little trick. And here's another one. This is actually even much more interesting. Is let's suppose I had the integral from 0 to infinity of sine x over x dx. Now this is really interesting because if you think about it, if x goes to 0, this is one of those problems where does this thing go to 0, 1, or infinity? Because sine of x is 0 and x is going to 0. And also, how do I integrate it? And so what we do here is we get a little creative, and we suppose that I of alpha exists where we're actually integrating e to the minus alpha x sine x over x dx. And in this case, alpha just happens to be equal to 0. Well, when I do that, what happens is when I take the derivative of this integral with respect to alpha, then I'm taking the derivative of the exponential term. And that's automatically going to kick out a factor of negative x inside the integral. So that's negative x e to the minus alpha x sine x over x dx. And of course, this term and that term cancel out, and I'm left with just a minus the integral from 0 to infinity of the exponential term, sine x dx, and then this is basically the same as the old one, but with lambda equal to 1. So it's minus 1 over alpha squared plus 1. And so that's my solution for the derivative of the integral. then when I want to solve the integral, I just have to take the integral of that. So I take that the integral of dA of alpha, d alpha, is equal to I of alpha, which is equal to taking the integral, or sorry, I should put a d alpha in here, of minus 1 over alpha squared plus 1 d alpha. And so now I have to solve the integral to solve the integral. And so this is going to be equal to some constant minus the inverse tangent of alpha. And so I'm not done, because now I have to figure out, well, what's this constant? I want to make this thing a complete solution. And so what I know is that if we take alpha equal to 0, then what happens is I of 0 is going to be just I. And remember, in I, we had that this thing, the alpha, is going to be equal to 0. And if remember, this is inverse tangent, so it's basically sine over cosine. And so if alpha is equal to 0, the inverse tangent should go to 0. And so this is just going to be equal to a constant. Right? And if you have alpha equal to infinity, then we know that in that case you have I of infinity. And for I of infinity, the exponential term here is going to drop to 0. And that's going to cause this entire integral to drop to 0. So that's going to be the integral from 0 to infinity of 0 sine of x over x dx, which has to be equal to 0 because the thing in the integral is 0. And that, we know, is going to be equal to c minus inverse tangent of infinity.
Is that arctangent?
No, inverse tangent.
It's inverse.
Yes.
So it's cotangent. But the inverse, then that integral doesn't work right, doesn't it? Okay.
No, that's the integral for inverse tangent. Evaluated from 0 to, it's an indefinite integral. So, if you, nope, it shouldn't be. Let me see. 1 over a squared. Yeah.
Like that's not
cotangent,
that's arctangent. That's supposed to be arctangent.
Let me check.
Yeah. It's got Google.
Well, what I have here is no. I think you're off a little bit. Let me. I'll show you. Because what I have, and where I got this is that. Where is this? Is that it's according to Shams, and this is 17.6.1. The integral of x squared plus a squared. is equal to 1 over a inverse tangent of x over a. No, this is inverse tangent.
But arctangent. Arctan or cotan?
Yeah, arctan.
Arctan.
Arctan, not cotan. So what's happening is here you've got a is equal to 1, and your x is your alpha, and you see you have an extra minus sign.
The point is that's arctangent, that's not cotangent. It's
Right.
1 over tangent.
Right. It's like inverse of tangent.
Okay, yeah.
That's why I put that on there. Yeah. If this were a minus sign, then it would be a hyperbolic tangent, inverse hyperbolic tangent. And so what this is basically saying that, oh gosh.
You said that it reflects sine over cosine, or cosine over
Or
sine.
sorry. Well, the reason why is because if you think of it as tangent of theta is equal to x over a,
Yeah.
then if x is equal to 0, theta is equal to 0. Because this is like saying
I mean, yeah.
sine of theta over cosine theta.
Yeah.
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 Yeah. So it's an inverse. So anyway, so because of that, we know that this is supposed to come out of 0, and we know that the inverse tangent is going to be at, when this is going to go to infinity, is basically when the cosine term here is going to go to 0. Right? And that's going to happen at pi over 2. So therefore, we could say that for the I at infinity, we should have something like it's going to be equal to 0, and that's going to be equal to the constant minus pi over 2. And because of that, we see that therefore this constant we're looking for is this pi over 2. And so if the constant is pi over 2, and the solution for the first integral is just the constant, then therefore we could see that the integral should be equal to pi over 2.
I think I missed what you said. Where did you get the pi over 2 from?
Oh, the reason why we got pi over 2 is because we're basically saying that this happens at alpha equals infinity. So if you take the inverse tangent of infinity, that's going to be equal to pi over 2. Because that inverse tangent is where the cosine term goes to 0. I'm going to do a quick example from Matthews and Walker too, where I just thought this was just kind of a neat use of this. We got an example here. Let's say I is equal to the integral from 0 to infinity of cosine ax over 1 plus x squared dx. And this is one of these problems where if you use contour integration, this is like really easy. But if you're not using that yet, which we're just kind of playing without it, then there's a couple other tricks you can use to do this. Now, one thing you can do with this is we can use what we had before, and we know that say I of alpha is equal to the integral from 0 to infinity of e alpha, or e to the minus alpha x cosine ax dx. And also, but what we can do with this is you can look at this with respect to this parameter a, and you could say, well, if I take the derivative of I with respect to a, then I can get the integral from 0 to infinity of minus sine ax over 1 plus x squared times x dx. And then I'll take another derivative of this, and I get the integral of minus cosine ax over 1 plus x squared, another x squared dx. Okay? And now, if I look at these two integrals, I could do something clever. I can actually say, well, if I take the original integral and I subtract off the second derivative of that original integral, then what I end up with is the integral from 0 to infinity of cosine ax divided by 1 plus x squared plus x squared times the same thing all integrated over x. And then this is basically going to be equal to the integral of 1 plus x squared over 1 plus x squared cosine ax dx. Right? And so, of course, this first term is just 1. So now I just have that my integral is I minus I double prime, which is equal to the integral from 0 to infinity of cosine ax dx. And then I can play around with this and I can add in my other terms. So I know, like I said, I know that a of alpha is equal to the integral from 0 to infinity of e to the minus alpha x cosine ax dx. And I know that that is equal to the alpha over alpha squared plus a squared. Sorry if the a's and the alphas get a little confusing here. So what happens now is I know alpha is equal to 0 in this case, right? And so alpha equal to 0 means this is equal to 0. So now I just have the differential equation to solve. And so now instead of solving an integral, we're solving an ODE. This is clever. And, you know, and this is pretty straightforward. Solution to the ODE is just simply going to be some constant times an exponential with, I guess it's with respect to alpha a. So when you take two derivatives of this, you basically get itself back. So a little bit different, but you know, you can actually do stuff like that. So the basic idea is that you know you can actually play around with the integrals as if they were objects, instead of just treating them like just their own separate unit. I had to point that one out because that's just one of my favorite examples from the book. And unfortunately, I didn't assign it to you guys for homework, so you guys will just have to dream about that one. All right, the next thing we want to talk about is the use of symmetry. Okay, and the basic idea here is that let's suppose you have an integral. And you're integrating over, like, say, the surface of a sphere. What happens is, you know, in science, you always have to be careful about your assumptions you make. And so this term right here is a solid angle, and basically means you're integrating around a sphere or something like that. And so you can actually break it up into a term involving a sine and a term involving cosine. So typically you'd see it like integral like this. So we integrate over the phi part, and sorry, I didn't mean sine and cosine, I meant phi and theta. And we're integrating over theta, and theta goes from, say, 0 to pi of sine theta d theta, and then you're left with this other term, 1 over 1 plus k dot r hat. Now there's a few things you can do to make this integral go better. Number one is that since you created the problem, you can choose how things are orientated. So you can choose your k so that it's pointed right along the z-axis. So k hat is parallel to z hat. And also, you know, your r here is just a unit vector, and these are spherical coordinates. And so what happens is r hat in the z direction is cosine theta. And so when you point k along the z direction, what happens is the dot product between k and r automatically are going to be this cosine theta term. And then also another thing you can do is you can use the fact that when you integrate sine theta, d theta, from 0 to pi, that is equivalent to integrating from -1 to +1 of d cosine theta. Because when you take the derivative of cosine theta, you end up getting sine, and then you kind of flip the signs so that everything else works out. So now what we do is we can take this integral, and it's going to be equal to the integral from 0 to 2 pi of d phi, and the integral from -1 to +1 of d cosine theta. And then you've got 1 over 1 plus k cosine theta. Because r is a unit vector, it doesn't put anything on here. And so now you're integrating with respect to cosine theta. And so often what people will do is they'll take their cosine theta and they'll just make it into some other variable like, say, x. And this becomes the integral from 0 to 2 pi d phi of the integral from -1 to +1 dx of 1 over 1 plus kx, which is a heck of a lot easier to look at. And it all just came by just simplifying. And so then when you're solving the integral, well, the first integral is easy. It's just going to be 2 pi because there's no phi's involved anywhere else. And then all you're really solving here is the integral from -1 to +1 of dx over 1 plus kx. And that is going to be equal to 2 pi over k times natural log of 1 plus k over 1 minus k. Okay. So it's pretty easy, pretty straightforward with that.
You don't have to change limits in there anymore?
What?
When you said that cosine theta is equal to x,
Mm-hmm.
That you don't have to worry about changing limits in that? Or?
No, no. It's d cosine theta is equal to x. Because remember, well, the idea here is theta has a range from 0 to pi, right? And over spherical coordinates. So what happens is that sine, when you integrate your sine of theta, you end up with a minus cosine. Sorry, other way around. You integrate sine of theta, you end up with minus cosine. And or you could think of it as, and so when you have minus cosine theta, then it's going to be, when cosine is equal to 0, it's going to be minus 1. And when cosine is equal to pi, since it's minus cosine theta, it's going to basically be either minus 1 or it's going to be plus 1. And anything in between. And so instead of doing that, you're basically saying, well, your d cosine theta is going to be evaluated from minus 1 to plus 1. Okay. So it's pretty straightforward with that. All right, let's have a couple more things I want to do. The next thing I want to mention is your old friend integration by parts, which is something that you use. It's easy to forget, but I think everybody remembers the formula when you see it again. UdV equals UV evaluated from, say, whatever the limits are, minus the integral of v du. So what happens here is that you have to decide what is u and what is v within your integral. So when you get a term, let's say one term involves an exponential, another term involves a sine or cosine, that's the whole trick of it, is figuring out which one is which. And typically, when you use this, and I'm not going to go into specific examples on it, but when you use it, you're going to use it in situations where, say, the UV term is going to disappear over your limits. Like if it's periodic or something like that. And that's when it seems to work best for integration by parts. Otherwise, you can end up piling on extra pieces here. But I'm not spending a lot of time on integration by parts, just wanted to kind of remind you guys that it exists so that when you're doing your homework, you remember. All right. Last thing I want to talk about are approximate solutions. Okay, and the idea here is this is stuff like the error function. Now we have 2 over square root of pi times the integral from 0 to x of e to the minus t squared dt. So basically this is equivalent to the first example we had if you take x to infinity. So if x goes to infinity, this should just be equal to 1. And so this is one of these things where you're trying to solve something on Mathematica and you put it in an integral or something like that, or a different equation, out pops Earth, something like that, and it's not an error on your calculator. So what this really means is that you can't exactly solve this integral. It's sort of like the zeta or the gamma function. But what you can do is you can, because this is an exponential term, you can use the infinite series stuff we talked about last week, and you can actually expand this thing out. And by expanding it, we can come up with an approximate solution. So we expand this thing, like using something like a Taylor series expansion or familiar series. And once you've expanded it out, it's very easy to integrate. And so all the zero terms disappear, and you end up with something like x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial minus x to the 7th over 7 times 3 factorial, etc. Okay, so what happens is, now that you got this expansion, if you have x less than 1, or less than or equal to 1, what happens is all of these higher order terms just sort of disappear because they're really tiny, and you can actually write out what is your solution just simply based on using the first few terms. In which case, you can numerically solve for what the solution should be. And that's, in this case, it's about the best we could do. Now, what if you have a situation where x goes to infinity? Well, if x goes into infinity, then of course the error function is going to approach 1, but it doesn't actually get to 1 unless you have x equal to infinity. So to find what happens here, you can take 1 minus the error function, and that's going to be equal to taking the integral, but you're actually subtracting off the integral. Does that make sense? Because you know that error function of infinity is equal to 1. So if you take the error function of infinity minus this error function, you're basically just going to take the limits of integration, you're going to flip them around from x to infinity, as opposed to from 0 to x. And then you can use your integration by parts on this. And so when you use integration by parts on this guy, what you end up with is e to the minus x squared over 2x minus the integral from 0 to infinity of e to the minus t squared over 2t squared dt, where my two parts here, obviously, one part is like 1 over t, and the other part is going to be e to the minus t squared times t, or something like that. So when you do that, you can end up kind of pulling this out. I think I may have that backwards, but so anyway, what happens is you do your integration by parts, you end up getting this one term. You do integration by parts again, then what happens is you have this first term, and then you have another term, e to the minus x squared over 4x cubed, and then you have a term from x to infinity of 3, whoops, this should have been x here, 3/4 e to the minus t squared over t to the 4th dt. And then you just keep doing that over and over again, n times integration by parts. And what happens is eventually you're going to take your error function and you're going to move the 1 over to the other side, and you'll see that this is going to be 1 minus 2 over square root of pi times e to the minus x squared, and then you're going to have a 1 over 2x minus 1 over 2 squared x cubed plus 1 times 3 over 2 cubed x to the 5th plus 1 times 3 times 5 over 2 to the 4th x to the 7th. Oh, this should be a minus sign here. And then you're going to have several more terms, and then you're going to have a minus 1 to the n minus 1 term, 1 times 3 times 5, all the way up to 2n minus 3 over 2n x to the 2n minus 1. And then finally, you're going to end up with another term, minus 1 to the n, and you're going to have all of these odd integers. Divided by 2 to the n, and then there's going to be a 2 over square root of pi times the integral from, say, x to infinity of e to the minus t squared over t to the 2n dt. And what's going to happen is, as n gets really, really large, then these final terms are going to get smaller and smaller, because you're dividing by 2 to the n, which is going to, of course, shrink it. But then also down here, you can see that t is going to be a big number anyway. And so when you integrate this t to the 1 over t to the 2n, that's going to be tiny. And e to the minus t squared is going to be tiny. So you can start ignoring terms after a while. And so because of this, we can figure out what the value of the error function is if we're talking about really tiny numbers or we're talking about extremely large numbers. In between, it gets a little bit harder. So if you're talking about a number like 1.5, then you're going to need a lot of terms here in order to figure out what it is, any accuracy. If you're talking about 1 billion, then it becomes easy. If you're talking about 0.1, then you can get that too. All right. So anyway, that's it for today. Like I said, this is not a long lecture, and even though we got a late start, we managed to get everything done. Everybody should remember I need your homework so that I have time to grade that, and I should have that back to you guys by recitation on Thursday. And I'll see if there's any questions. We have lingering. The idea of Thursday's recitation, I'm mostly going to go over the homework that was not graded by them, and any other questions that you guys have over material, just let me know. Yeah, it should be on Blackboard.